So we're going to start today with the first candidate is Maria Romero-Pena. She is a PhD candidate at the University of Saskatchewan in Saskatoon, Canada. Got some really good friends that live there. She is also a professor at Escuela Superior Politécnica de Littoral in Ecuador. So Maria is in the PhD program at Saskatchewan since 2017 under the supervision of Dr. Supratim Ghosh, and her thesis is development of stable liquid water and oil emulsions by modifying emulsion aqueous phase interactions for food and related applications. And the title of her talk today is Viscoelastic Improvement of Water and Oil Emulsions for Food and Related Applications. So thank you, Maria, for joining us.
Everyone, thank you for attending my presentation. One of the current challenges in the food industry is the development of low-fat margarine type table spreads with glycerol monooleate. So this type of emulsion with glycerol monooleate are very complicated systems to stabilize. For example, here, this emulsion it has no additive in the aqueous phase. As you can see, it's completely destabilized. However, this emulsion contains low methoxyl pectin in the aqueous phase, and this emulsion reached near the 80% of stability. So this led us our project to develop a viscoelastic improvement of water-in-oil emulsions for food and related applications. So to modify this liquid state to a solid-like properties. So now I'm going to show you the methodology that we use. In the aqueous phase, we add 1.5% of low methoxyl pectin, LMP. In the continuous oil phase, that was canola oil, we add 7% of hydrogenated soybean oil, which create a crystal network to give support. Then GMO and water was at the constant ratio of 0.065. So we keep constant because we want to remain similar water droplets size. So LMP emulsions we developed in 4 different levels of water, 20, 30, 40, and 50%. And control emulsions had the same ingredients without LMP. So control emulsions contain 2 levels of water, 20 and 50%, and all the emulsions were prepared with 2 steps of homogenization. First, the rhododestator, and second, the high pressure homogenizer. So now let's see the results. Here are the stability results on day 30. For control emulsions, 20% water, it showed a flow. For 50% water, there was a phase separation at the bottom, as you can see here. However, LMP emulsions did not show any separation or flow. So now this is the apparent viscosity results, which is a flow resistance. We give us an idea about that. So viscosity showing Pascal per second, and as the shear rate increase, the viscosity decrease. This behavior is shear thinning viscosity. Comparing day 1 to day 30, almost all emulsions remains in value or increase a bit. However, control emulsion with 20% water show a significant drop. This was related with this flow in the stability test. So now for storage modulus is G prime is related to the elastic capacity of emulsions. So just for comparison purposes, I'm gonna show for at 0.01% of strain. So all the emulsions show an increase, a G prime increase with the rise of water content. As you can see here, LMP, however, and this is for the control and 50%. However, control percent 20 show a significant drop compared with 20% emulsion with containing LMP. Now the crossover strain, it will give us the strain required for gel breakdown. So here is showing the crossover strain versus the water content, and you will see that for day 1 and day 30. So all the LMP emulsions show a proportional increase with the water content, compared with both control that show significantly lower values. This indicates that LMP form a higher gel strength in all emulsions. So now I want to show you the mechanisms behind this. So 20% water-in-oil canola emulsions with LMP form a viscoelastic gel due to the less water droplets. However, without LMP, there was evidence that it was a liquid-like flow due to the emulsion destabilization. With the highest water content, 50%, water-in-oil emulsions with LMP form a strong elastic gel due to the droplet aggregation and packing. However, without LMP, definitely was a strong gel, but mainly due to the partial release of the stabilized water droplets and predominant fat crystal networks. Overall, the increase of water content containing LMP and HSO with GMO allowed the development of viscoelastic properties of water-in-canola oil emulsions, being an innovative alternative for low-fat spreads. Thank you so much, and I'm gonna answer the questions after in the Q&A.
Thanks, Maria. Excellent presentation. We're going to open questions up to our judges now for you.
Sure,
well,
Doug.
Amanda, yeah, go ahead.
Okay, thanks, Maria. Really nice job. You exemplified your data in a really effective way and highlighted the problem that you're challenged to tackle at the very start. So really nice work. One of my questions was, what motivated your decision to use low-methoxypectin in particular?
Well, we tried different molecules that have hydroxyl group donating agents. So we have a previous research where we identified that the pectin was the best molecule that interact with GMO at the interface. That's why this is a further research after that.
Okay. And do you expect that you might see differences in the stability of your emulsions based on things like pH if you were to put this into a food application?
So far, we have worked only with the addition of the hydroxyl group donating agents, but definitely it's an idea that we can do it in the future, do more work in the future. Yeah. So far, it's only for pH 3.
Okay, thank you very much.
Yeah, thank you.
Yeah, hi, Maria. I think it was also great. I love the way you drew the mechanisms and all. I think it was very depictive. Apart from the pH questions Amanda had, my question was, typical margarines and spreads always contain a bit of protein for a faster flavor release emulsion breakdown. So because with all the emulsifiers, it can be a very tight emulsion, thinking practical application in mind. So have you ever tried adding a little bit of skim milk powder or a dairy protein in the water phase? Or do you expect any destabilization effect from that when you add protein?
Well, I have read studies that they have been using another like proteins, like you mentioned, and forming like a network too. However, now it's like our research is basically because in studies before it was found like canola oil emulsions or vegetable oil emulsions are very complicated systems to stabilize. So our idea was to find what was the reason and try to solve this problem. And we found that it was for the hydroxyl group donating agents, that GMO is a small emulsifier but need this bonding in like enhance the bonding, because it is a bonding that happens, but GMO distort at the interface. So far we are keeping our project like trying to solve that problem that have been happening for many years. So, but definitely it's a good idea for the future for sure.
Yeah, because I'm from the industry and all the fantastic work you guys do. I always want to translate it back to the industry, to the consumers. So I can enjoy that as consumers, because this can be a great application. And one other point, you have fully hydrogenated soybean oil, which would melt very steep. I mean, like it doesn't melt that well. So maybe in some cases, have you tried something that melts more, more steeply, more smoothly?
You're right. So far now we did analysis of solid fat content in this project. I'm not showing the data here, but definitely what actually we propose in the future is not using hydrogenated soybean oil. It's actually using another type of emulsifier, like particles that enhance the network, like a substitution, partial substitution, right? But yeah, definitely something that we have to look in the future. But there's so many things that we want to do after this.
Absolutely. Sure. Thank you.
Thank you. Thank you so much.
Okay. Hello, Maria. Also from my side, big thanks for your nice pitch. It already solved some of my questions. So from that perspective, it was already enlightening. You said you're targeting the table spread or the fat spread application. Did you ever also include a reference, a commercial reference of a table spread? And do you think your rheology values that you obtain are close to commercial applications?
Good point. Really good question. Definitely something that we want to do, but at the beginning it's like, you know, we were trying to change something that was liquid to solid by this solution. So I think all the questions that you made me today open to more stuff to do, right? Comparing, analyzing within our compounds. So, but I think it's a good start. So far we haven't done, but
yeah. Okay, you use the GMO as an emulsifier.
Yes.
Could you shortly tell a bit more about that choice?
So glycerol monooleate is a amazing emulsifier, have very good properties at the interface. In general, we want to choose GMO because, you know, PGPR has been an emulsifier that have been used for so many years in water-in-canola emulsions. But in Canada, this emulsifier was banned since 2018. So there are some, the last maybe 10 years, try to smoothly change that part, right? So that's why we went to this type of emulsifier that is also have a very good interaction, but the structure is very small. So we try to...
Do you think there is an interaction with that emulsifier and the fat crystals?
GMO has been identified in previous analysis, like it helped to localize the crystallite interface. So if the crystal is not sulfate active, the GMO will help in the polarity and kind of surround the water droplet.
Yeah. Okay, thank you.
Thank you.
Yeah, Philip, Supratim loves GMO. I know a lot of Supratim's work is based on GMO. I've had discussions with him. He loves it.
But it has a reason.
Yeah. I know.
Joking. Thank you so much.
Fantastic. Thank you, Maria, very much.